Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 379. Maximize the number of partitions after operations. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. To be honest, I don't have a great solution for this one, or at least not a tight solution for this one. But I'll go. If you watch the live portion of it, you'll kind of see the genesis of what happened. I ended up solving this in about, was it half an hour? Half an hour for 35 minutes ish. But to be honest, by the time when I submitted, I did it in a YOLO way, and we'll kind of go over why I did it in the YOLO way. It's not a pure YOLO in the sense that like I just had no hope, but I had a little bit of a hope and a little bit of an inkling. But we'll go over why. And let's go over the problem real quick. And the idea here is dynamic programming with brute force. That's basically the really idea about it. And the hard part about this is going to be the proof, which, you know, it's a tricky one for sure. And I'm going to just paste some code that I have before. I mean, I kind of had more code about this because I was thinking about it another way. But one thing to notice is that so I had this code before. Okay, let me actually go over my explanation real quick, and then I'll kind of go over the proof and the evolutions of stuff, if you will. But basically, this is the dynamic programming, and was it last week? Yeah, last week we kind of, I think it was last week. Definitely let me know if I'm wrong about that one. But yeah, last week I think I did a dynamic programming on bitmask video. Definitely go back to that one. Maybe I should release it separately as well. But definitely if you have a strong idea of bitmask dynamic programming, then that would help you a lot. Just because, you know, and because it is in last week's video. It was last week, right? I'm not going to go over bitmasks too much today. Hope that makes sense. But basically the bit mask is just to keep track of all the things that we've seen. Basically, each bit of bit mask tracks the paste it real quick. Tracks if the character, some character C has been used, right? So some character in the alphabet. But yeah. But basically, yeah. And let's go over each one. Index is obviously 0 to n. It is just the suffix of the thing. Used is whether we did what was it called? Oh, we did the operation. Use the operation. And count is count doesn't really do anything. It's just it's just a very short way. I mean, I probably didn't need it per se, but it's a little bit of an optimization. But count is just the number of ones in bitmask. So maybe I don't really need it per se, but yeah. And basically for each one, we have a couple of choice. Well, we have, I don't know about choices, but yeah. But it is kind of brute force in a way. It is just basically saying, okay, if we haven't used, I converted these to bitmasks from the character. So you know, so you have to take a look here. But otherwise, if we haven't used this character yet, then what happens? Then, well, then the count goes 1. That's all it does, is that we keep track of the bit mask, and you know, there's no choice here. We just have to use, you know, this is not using an extra thing. We just pause the current thing, and then else we have b of index. We, you know, because if it's greater than k, then now we have a new new partition with only this thing and yeah, with only this thing, and you have one which is the number of count, because this only has 1, and then you plus 1 on the number partition. Like we said, we create a new partition, right? Otherwise, if we have used this, then the mid mask doesn't change, the count doesn't change, and we just go to the next character. And then now, if we haven't used our operation yet, then we can change. If we haven't used our operation yet, brute force on changing it to one of the 26 characters. And it is pretty much as as you think it goes. It just brute force. But yeah, this is just brute force. We convert this to a bit mask, and then same idea here as before, except for we converted the use to true because now we converted it. You could also maybe made an if statement on whether they're the same, but I think that it doesn't matter, right? Because it's strictly suboptimal, so that wouldn't change the result. But yeah, basically we take the bit mask here, using it and not. So this is way brute force, way just kind of scanning it through the way, but that's basically the idea, right? Again, it's I'm not trying to say this is an easy problem, but the idea is easy once you do it. In the sense that if you understand bit mask, then this this makes sense, and it's not even a bit mask DP, because if you kind of it just uses bit mask, but it's not a bit mask DP. Because in this one, if you kind of naively calculate the complexity, and this is the hard part of the problem, the proof part, and I think a couple of people near the top, or at least from what someone told me, they didn't really do a hard proof, and they just kind of YOLO'd a little bit. I mean, maybe they have intuition like I did. So yeah, as I said, 0 to n for index, use the boolean, so 0 to 1, or like just 2 possibilities, I guess, maybe another way of writing that. But bit mask can go up to 2 to the k, right? K is the input, yep. So that is actually a lot, and count could be also k. So at a naive stand, even though everything is O of 1 here, actually O of alpha here, whoops, O of 26 here. So this is going to be O of n, but n times 2 to the k times 26, which is actually a big number because k could be 26. So the question is, why is this fast enough, and why did I YOLO this, right? The reason is because I spent a lot of time on this problem, and when you look at the live portion, you'll kind of see I try to do a lot of different things. And the first thing that I noticed, and I kind of wrote a sliding window part about this, is that let's say you're not making a change for this partition, right? Let's say let me actually do a paintbrush real quick. And I kind of wrote code to kind of, but it also makes sense. Where's my pen? Oh, there we go. The proof is actually the more interesting and hard part about this. But basically here you have, let's say you cannot make any operation change, then that means that, this is a terrible straight line. I should just use the straight line thing. There you go. It's a straight line. Right. That means that without any changes, you have, this goes to here, this goes to here, and then you can pre-calculate this, right? So yeah, so basically, for example, this has 4 partitions. So the idea behind this proof, this dynamic programming, and it's not a strict proof, but it is the proof that gives me a strict. Gives me a way to YOLO, is that everything is local. What do I mean by that? Is that when you do the one operation, it can only change a few things, right? And what I mean by that is that, let's say you change this character right here. Well, that means that in the worst case, it will only it will only change all the ones that go after. Is that true? Maybe it's not quite true with the locality, but the idea is that once so what I did was that I pre-calculated all the maps from the beginning of a partition. That's the other way of saying it, maybe. So for example, for here, we'll always end up here. Maybe here, we always end up here, and so forth, right? Dot, dot, dot. But that means that for every partition, it only matters where you end the partition after a change, right? So that means that, let's say you made this change here, and now your partition now goes. Your partition looks like this, right? Well, what does that mean? That means that, well, you only have to calculate this to the next thing once, because everything else is already going to be calculated, right? So that means that, yeah, this only needs to calculate it once, because here you can think about the bit mask as 0 and all these other things, right? And as a result, because the bit mask is 0, the count is 0, and as a result, it doesn't matter how you get here, so, as long as you get here, and you only need to pre-calculate this once as a beginning of partition. That means that the yeah, that means that for the bit mask, the only thing that happens is that you change if it keeps on, you know, like, how do I say it? That means that, for example, if you change, I don't know, let's say you change an A to a C, which doesn't exist, and then an A to a D, which also doesn't exist, they're only going to differ in this part, and then every other part is going to be the same. So that means that, you know, we calculate all these, and of course there's also a lot of other overlaps as a result, meaning like we change an earlier thing to C or D, and then the bit mask kind of matches that way. But as a result, then now we only have n beginnings, right? So that means that there are not that many possible states for you to kind of change. But that's basically the idea that I kind of started off to build this YOLO solution, if you will, is that we have this end thing, and then the rest we can also check it, you know, one at a time. Yeah, that's pretty much the idea. I don't think I've made a great explanation or proof, but that is kind of the hard part about this problem, is that proving the bounds. Like, you cannot get too out of whack even with k is equal to 26. And actually, the funny thing is that if k is equal to 26, most of your changes don't change anything anyway, right? So actually, it's not even a maximal case, because, or it may not be, because when you change something, like yeah, you may have changed it earlier or later, but like, because it just eats up everything, it gobbles up everything, that there are actually very few cases. And because you can only make one change, most of the changes don't propagate forward, right? So everything is very local in that regard, and yeah, and that's pretty much basically it. And a lot of them kind of repeats itself as a result. Hope that's a good enough explanation. I don't think that is a great explanation, to be honest, but I think this is, you know, that was the mindset though, of, you know, writing it this way, and then kind of be like, I think maybe we could actually YOLO this, and basically that's what I end up doing. Oops, and that's basically what ended up happening. So yeah, that's pretty much it. That's all I have for this one. Yeah. Let me know what you think. Let me know how you did, and you could watch me solve it live, including the progression. And I tried a lot of different things in that 35 minutes, because writing this would probably have taken like 5-10 minutes if I really believed it in the beginning. But most of the time it's on the proof. So yeah, that's all I have for this one. Let me know what you think, and you could watch me solve it live during the contest now. YOLO. Okay, good. How am I doing? The 5 minutes kind of sucked. Should have done that much quicker. Good job, Chi-Chi. Okay, focus. Don't look at Chi-Chi. Chi-Chi's been on hot streak there. But S and K. You have a string, you have an integer. Choose the longest prefix of S that contains at most K distinct. delete the prefix. Change them. And you have one operation. Okay. Maximum number partition. Okay, so you have k is equal to 2. It's just dp, right? Maybe? Is it a fast enough dp? I don't know. I mean, it's going to be n squared if you're not careful. Oh, it's maximum, not minimum. What? Oh, it's... You have to choose the longest. So it's not a choice. This shouldn't be choose, this is fine. Right? That would be an easier way to write it. Okay. How am I doing on time anyway? A lot of people haven't done Q2 yet, but... Okay, so it's forced, otherwise this wouldn't make sense. K is 26. Why is K 26? Does that matter? Oh, I guess distinct characters. Okay, fine. Is it still DP? To do binary search, but that's not very helpful, is it? Well, you could get the solution for the rest. Okay. So changing a character only changes the suffix. Yeah, changing a character into suffix. So you could calculate all the prefix answers. And whether we've changed it yet. Maybe. Let's say we pre-calculate all the next characters, right? Can we still put force that way? Oh no. Can I look at this backwards at all? I don't know if that's easy. This is a 7-pointer. I'm here somewhere. Now. next unique character. Actually, that means that you only do 26 things because every time you move. So the number of partitions, no, that's not true. It's 26 per partition. And then you have to kind of loop through it again. Huh? You have a sorted list. Allows you to do it once, but then you still have to keep on putting stuff in. So I don't think that's quite the same. I don't really have an idea. Someone got it right already, though. Is it a caching problem? It was like a caching problem, or like not a caching problem, but like a problem where you save on calculations. 10,000 and log in times alpha. For each character, you go to the next one. Is that too expensive? Sliding window? Oh, sliding window. Why did I forget about sliding window? So we can do sliding window to calculate. To right. It'll be like a reverse sliding window. And then now we can brute force the rest just based on the maybe? So this is basically well, the counter is less than K. Something like that. It's at most, so it should always go to the end. Okay, fine. And then now left goes to the right, right? Left to right. So then now to, and then so this includes everything from left to right, and then now we move left. How do we remove left? Oh well, +1, but then now we move right, and yeah. Okay, and then now we wrote this map. So then now all it takes is for every cell. Can we brute force now? Yes, fine. Then maybe 26 times n times log 26. Yeah, okay, maybe fine. Only 2 people got it right. Alright, let's print it out real quick. The 2 unique is 0 to 2. Okay, 1. Is that right? That's not right. This isn't right. Because basically we want to keep on going if this is inclusive, right? Because we have to. So okay, so this is adding new ones. And maybe I need another way and separate encounter 10. Okay, then now it should be all 5s, right? Okay, that's good. That's good. I mean, it's not great, but it is expected. So 1, it goes to 2. Okay, and okay. Okay, and then now what are we doing? Now, did Chi-Chi finish? Well done, Chi-Chi. He's on the roll. I don't know how to do this, so I don't know. In fact, I mean, all but 3 people know how to do this, so I don't feel that bad. But it, yeah. Okay. So then now we just have a next thing, right? Okay, yeah. That should be fine. Okay, right? And then now, what are we doing? Nope. Okay. Is this right? Looks very well. Oh, that's why. Should have one. No, it should have an A. What is going on here? What? 4 0. Yep, that makes sense. 0 0 also makes sense. Oh, whoops. Okay. I was wondering. Yeah, this is always awkward to print. But okay, you have an A and you have a C. So the next A is at 1, next C is at 1 or whatever. Said it wrong, but whatever. Okay, so that's good. And then now, okay. Now we brute force, I guess. Maybe? How do we brute force? Actually, kind of thought about it the wrong way. Does it matter what we change? So it only matters what we change within a partition, right? What is this 2 thing again? Oh, that's if we're starting from here. This allows us to... Well, this allows us to pre-calculate the thing, right? So we have to get a suffix from that. But how do we do the other part first? So let's say you have this partition. Is it DP? In a way it's DP, but yeah, I guess DP is fine. I don't know if all this is necessary, but this is force. Okay, so then now if used, then we just return goal. 2 of indexed used, right? Otherwise, this, I'm just curious here. Just making sure that this doesn't do anything crazy. Also, okay, reasonable running time. May not be most complex, but okay. Otherwise, we want to say, oh, is this +1? Just curious to see if this, okay, so it gives us 1, which is true, also 1, which is true, this is 3, also true. Okay, that's good. Or like it's what we expect, but now we want to change one of these. If it's used, we have no choice. Otherwise, we can choose whether we want to use it or not. So you can do best is equal to code 1, or now we have to change one of the characters. It's actually kind of hard, isn't it? Because basically we want to, I guess if we're going to do a thing iteration to it, then maybe I don't know how to do it. Is it deep copy? Does that work? Make sure they're not pointing the same reference. Okay, they have different references. Okay. But that's going to be 26 squared then. If I do it sloppily, how would I even do that? Because you can extend a thing. Oh wait, no, you can't. Because okay, let's say if you change A to B. Which you actually do want to do, change a C to B or something, right? And it actually matters which one you change to, huh? It's not just a set collection thing. I don't know, really. I don't know that I know how to do this. Huh. We have 45 minutes. Like, if we change each partition, can I abstract it really? Like even changing an A to a B actually increases the K, right? So, or the number of things. So it's not even, I thought I could just change. And even changing this A to a B could make this 2, even though it's not optimal, but and here changing an A to a B, does that do anything? No, it can only make it worse. So you always want to change one of these, and you always want to change the first one. I guess it doesn't matter if you change the second one, but that's still 26 square. What's 26 square? 676 or something. That's cutting it close. 676 times 10,000 for Leetcode anyway. Is there another way to think about this other than coding? So you want to. I'm just trying to think about how to do brute force in a smart way, but I don't think I'm doing it. Is there a way to do one character at a time? If I do one character, how would that look? If I change this A to B, what is the recursion? About some crazy bit mask thing. I'm gonna try something really crazy and just kind of see if it works. I just don't know how to do it with the way that I had it structured. Right. I'm just gonna copy it somewhere so I have it in case. I can't prove it, so that's why I'm just trying to YOLO it. Ask and finish it, so yeah, this will be one. Okay, and then now if not used, then we can just use it. Do we always want it to be a new one? I don't know. Oh, but you have to subtract it and not use the. Oh no, you just don't use the current one. That's fine. Right? Yeah. Okay. Fine. Yeah. Whatever then. This is more of a YOLO attempt, to be honest, because I don't know any other way. No, I got 2. Why did I get 2? If it goes +1, then no, it's not. Oh, this is a little bit awkward. Okay, so yeah, this is awkward. Okay, fine. Okay. Because I can't do it this way, but else if this is greater than k, then now we keep everything, but now we do 1 plus 1. But now that means that we always terminate. No, we don't terminate. No, this is fine. Yeah, okay. But now I have to do it here. This is actually J. Excuse me. But is it fast enough? I don't know. That's what I'm worried about. Actually, I mean, yeah. I mean, I don't need this, and I don't need this, so maybe that'll be faster. But I don't know, to be honest. This does not look good. And a lot of these are like, you know, but okay. How do you do random again? Maybe I just do like it's not random, I know, but Alright. I mean, I'm just gonna YOLO. I don't know that this is gonna work. There's something about that's a little bit silly. I don't know. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between, the explanation, whatever. Stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.